Hello, everyone. My name is Luis Sentis, and Dimitrios asked me to record this lecture on whole body control. I am a faculty at the University of Texas at Austin, and I developed whole body control in the mid 2000s. I believe it had started to have an impact in practical use in the early 2010s when the DARPA Robotic Challenge took place. And since then, it has evolved and it's been evolving into different avenues, including optimal control and MPC, model predictive control, and of course also model-free optimization using, for instance, reinforcement learning. But I think this lecture is useful for all of you guys to sort of learn the foundations of this model-based approach, and then later on you can take it to the next level. Well, it's a pleasure talking to you guys, and let's go into the materials. And for that, I'm gonna share my screen. Okay, so just give me a second. And here we are. All right. So again, welcome. That's a lecture on whole body control. It was developed for humanoid robots since those were the kind of systems I was working back in during my PhD. But it can be used for other type of robots. It can be used for free-flying robots with robotic arms. It's normally oriented towards systems with many degrees of freedom. So you wouldn't naturally have vehicles with like limbs and arms and legs and these kind of things, but you can apply it to mobile manipulation as well, and even underwater robotics, if you will. And again, my name is Luis Sentis, and today is March 8, 2021. The way it's going to work, I'm going to go through the lectures that you have access to, and I'm going to highlight important points. It's a long set of slides that I taught for one of my courses in human-centered robotics over a period of various lectures, and we're going to condense all of them into today's lesson. To ground ourselves, we're going to define human-centered robots. They are robots that often have high mobility manipulation capabilities and are aimed at collaborating physically and logistically with people, with us. We're going to define whole body control. It's a feedback optimization technique that allows to track multiple motion trajectories and solve complex using priorities in robots possibly under multiple contexts. Context is important and complexity is important. Let's switch to modeling legged and other humanoid and human robots as a whole. So I'm going to remark that legged robots are hybrid systems in that a single model doesn't describe the transition dynamics. And we know that this is hard because now we have to perform optimizations with this change in models. So definitely an interesting topic. And then our remark too is that legged robots are floating systems as well, in that they are not rigidly attached to a base frame, for instance. And that also entails other type of treatment that includes, for instance, conservation of momenta. Let's go into kinematic and dynamic modeling. Kinematic are determined by robot joints and contact interactions. Therefore, we represent humanoids as free-floating systems. You know, they can move anywhere, but they are pushed on Earth against gravity. They are against the ground through gravity forces. And here we see that sort of model. Sorry about that. So we see a robotic joint, a robotic system with multiple joints marked here with the blue circles. And then these are virtual joints. These are a spherical joint and represent the position and displacement in space. And those are sort of linear joints. So a total of 6 of them representing the SO3 configuration of the robot, the SO3 standing for symmetric orthogonal matrices. And that leads to us defining floating base coordinates. Where is the robot in global in space with respect to a reference frame? We use XB for position configuration of the base of the robot, and those are the linear configuration, and this is the rotational configuration. It can be Euler angles, it could be other representations as well. We're going to define now generalized coordinates. Is the minimum set of coordinates that define the entire state of the robot, and that needs to include the base positions and the joint coordinates Q. So it is a vector with dimensions 6 plus n, and Q are the robot's joint coordinates, normally the actuators or the output of the actuators. And to continue our modeling, we're going to consider the kinetic energy of the entire system, and that's a summation of all the linear kinetic energy of every linkage I, link I, plus the rotational components of link I as well. We're going to use for a second what is called a twist theory, in which we define velocities that includes the linear component and a rotational, an angular component. So, psi I, it would be the twist of link I is equal to the twist that defines the base. These are the velocities and linear and angular of the base, and the joint velocities multiplied by the Jacobian of link I. And a Jacobian is the partial of the coordinate we're considering. In this case, is the position and rotation of link I as a function of the joint configurations. Okay, that's the Jacobian matrix. And this defines the differential relationship of the link with respect to the generalized coordinates. Okay, another step that we've passed. Now, for a second, we're going to define Lagrangian formalisms. Some of you might have seen it in classes in dynamics, for instance, in which we define a Lagrangian operator L, and is equal to the kinetic energy minus the potential energy of the entire robotic system. Okay, and by Lagrangian principles, the time derivative or the rate of change of the partial with respect to the generalized velocities minus the partial of L with respect to generalized coordinates, it can be proven to be equal to the non-conservative forces. Okay, that's a nice theorem from Lagrange. And again, psi b, I use psi for this Greek letter, is the base velocities, linear velocities, and angular velocity of the base. And in our case, we're going to assume that there is no conservative forces. There is no non-conservative forces. So for a moment, we're going to assume there is no friction, there is other non-linearities, but of course, there exist, and we have to take them into account one way or another in realistic systems. And also, we note that the potential energy contains the effects of gravitational forces on the links, which end up pushing the robot down on the floor. And then it can be shown that the solution to the Lagrangian rigid body equations that we just formulated above yield this equation. We're going to call it the whole body equation of motion. Accelerations, generalized accelerations are multiplied by something called the mass inertia metrics in joint space. And they have effects due to centrifugal and also Coriolis effects, gravitational effects, contact forces on the limbs in contact. And finally, these tau are the policy for the motors, or the the torques commanded to the motors. But because we have floating coordinates, we multiply by the matrix ut, and ut is here, u is zero identity. It's a selection matrix selecting actuated degrees of freedom because of what we said, as floating doves are virtual, okay? And again, tau are motor torques, or it could be hydraulic actuation torques in robots with hydraulic actuators. It could be linear forces as well, or torques, depending on what kind of actuator you have. Also, I want to remark here that torques tau are not motor commands. Well, I know I said that just above, but they are not really motor commands. But they are the joint torques, okay? And those differ because between the motor and the output joint, there's normally a transmission system. So the true relationship between actuation commands and joint torques is complex and rather limiting, and that has to be contemplated carefully. All right, so we're going to go into the next portion of this theory, and that relates to dealing with context, which is a feature that we see during locomotion, during robots with legs, or context when interacting with an environment. We're going to assume for a moment that contexts are fixed. For instance, in locomotion, this happens during the support phase. When you step on the floor, once you land the foot, we're going to assume that it stays there. And that at the kinematic level, it can be written that the rate of change of the twist of contact, the linear velocities at the contact point and the angular velocities at the contact point is equal to 0. Basically, accelerations are 0 at the contact point, okay? And velocities should be 0 as well. We're here playing with the dynamics, which is second order interactions. Okay, so this model allows to solve for the contact forces or the contact wrenches by going back to the whole body equation that we developed before and imposing that constraint, and analytically you can obtain this complicated equation that tells us is a model of what the contact forces are as a function of the joint torques and gravitational and Coriolis effects and other and generalized accelerations as well, okay? And here we started seeing a little bit of heavy use of operators. JC bar is the dynamically consistent inverse of JC, the Jacobian at the contact points, and is defined as this complicated formula here, A minus 1 JCT, JCT, A minus 1 JCT, everything to the minus 1, okay? And in particular, that last term is also called the mass matrix in contact space, okay? The perceived inertia at the contact point. So now that we solved for FC, and it had appeared in first place in the whole body dynamic equation, we can now bring it back. So we can plug back FC into the whole body equation of motion, and it yields this new equation, okay? And now we've got rid of FC. FC has, in a way, has been abstracted to projecting the torque in the null space of the contact points, the null space being defined by the identity matrix minus the generalized inverse of JC times JC. And it can be proven that one of the properties of the contact consistent null space is that right multiplying the Jacobian by the null space, it renders 0. All right, so let's go a little bit more farther. We're going to make a remark. There is some sort of contact redundancy in many types of robotic systems. In particular, those with flat feet, which representing here. And if we focus on the base or the arms, for instance, we can go this route. We can use an estimate of the free-floating configuration, and then we can obtain the differential kinematics of the base or the arms or whatever we need. But we can also do it from the legs perspective, from here and here, because they are rigidly attached or standing on a floor. So there is a redundancy for coming up with base kinematics or arm kinematics. And that, in other words, it means that we actually don't need to know the free-floating configuration. We can get all the information from the context. So X-base is not needed because we can find all kinematic information using only Q, which are the robot joints, the leg joints and the arm joints. And we're going to make another remark here that this statement is holds if the dimension of the contact ranges of every contact range for every limb I is greater than NLI, and NLI is the number of joints of the ith limb. If this is true, then you have this kind of redundancy on the configuration, on the kinematics, and then you can express everything with respect to contact coordinate. Okay. All right, so we're stating here, therefore, because the robot is constrained by the ground, the position of its base can be derived from the position of the robot joints alone. How do we write that as a formula? Okay, we're going to say that the generalized velocities in here is the twist of the base, and the joint velocities, it belongs to the image or range of the null space of contact. That's identical to the statement that we make above, with star denoting constraint values, okay? So of all the possibilities of the generalized velocities, we're picking those that live in the manifold inside the null space of contact. And that's what we call it the star superscript, okay? You can further project that image by only considering joint velocities, and it can be shown that joint velocities is equal to generalized velocities multiplied by UNC, and again, the star here means constrained joint velocities, okay? We're sampling only the values that are in the null space. That gives us the constrained generalized velocities, and now we're multiplying by U to obtain the joint velocities, constrained joint velocities alone, okay? More importantly, we can invert this previous equation. Q dot is a function of the generalized coordinates, and now we obtain the opposite. The generalized coordinates are equal to something that is a function of the joint velocities, and for that we use this inverse UNS, which we call the dynamically consistent inverse of UNC, and it has this complicated formula that we're not going to delve into it. Now notice that here we're using not -1, we're using plus for the Moore-Penrose pseudo inverse. And the reason is because in some cases we have ill-conditioned context, and then we have to define something that is more general than an inverse of the matrix. All right, we have some of the background. We still don't have the control of tasks, but we have the effect of context, and we have to start moving towards the practical application. And that we're going to define whole body behaviors. Because legged and humanoid robots have multiple limbs, the behavior involves each of them following a different trajectory. Okay, so whole body control is a trajectory tracking controller. It's a feedback control policy. So often we call trajectories tasks. That's the lingo that we use in operational space control in whole body control. Okay, so behaviors are also referred as multitask control policies. Okay, so for instance, here we have a depiction of a robot it has a nail gun that is inserting nails in this sculpture or something like that, and it's assembling these autonomously. So we define a skill, what kind of task it has to control. It has to control the center of mass or center of gravity, not to fall. It has to control the gun force, to apply a specific force in this sculpture. It has a hand orientation because the nails have to go in certain orientation. It's looking to do the servoing, the visual servoing. So it has a gaze control of the head, and then it has a posture that controls in general the overall attitude and height of the torso in general. All of them have to be tracked simultaneously, and that's the main challenge and what is exciting about whole body control. So let's go, and now we've grounded ourselves into tasks. Let's consider task kinematics and dynamics under contact constraints. Okay. So as we said, we define behaviors as a vector of task coordinates with tasks like we saw them before. I call them skill and behavior. I use the same. For me, they are synonyms for our problem. And now again, using differential kinematics, we can obtain a Jacobian for every task coordinate as a function of the generalized coordinates, as a differential with respect to the generalized coordinates, such that we have this differential relationship. Okay, this kinematic velocity of the task space is a function of kinematics in the joint space, in the configuration space. More on that, one of the books that you can read is the Lynch and Park, David Lynch and Prime Park, very good book on kinematic dynamics and controls of robotic systems. And then, here to give you a bite, those of you who have not been exposed to simple kinematics, consider a simple robotic system. It's a chain robotic system. This one is not floating, it's not in contact. The end effector kinematics can be expressed with the joint kinematics. And now, the task can be obtained by nonlinear projection of the joint coordinates. Okay, so it's a nonlinear projection to just give you an appreciation of what is a Jacobian exactly. So let's go back to task kinematics. We said that is a function of the generalized velocities, but the generalized velocities, if you recall, when they are constrained, they are a projection, an inverse projection of the joint velocities multiplied by the constraint matrix UNC bar. And therefore, if we plug this in on this top equation, we obtain a relationship between task velocities and joint velocities, which is great. So this equation, in a way, it captures things like the effects of the reaction forces, and also it captures the effects of a conservation of momenta as well. And that operator, this JI UNC bar, we are going to call it JI star, and is called the support consistent Jacobian. Okay, we take the Jacobian, we'll multiply by UNC bar, and we take this variable, this new operator, and that comes from free-floating systems research that was done in the 1990s and early 2000s, where conservation of momenta, like for instance in a satellite with a robotic arm, you need to account for the conservation of momentum. And the J star notation, it comes from the generalized Jacobian of that body of research. And I took it to the the area where contacts occur in the system. All right, so far so good. We are progressing quickly. And we're gonna go to the next stage, connecting to balance. So we are exploring bits and bytes that make whole body control what it is. And we'll put everything together into a control framework once we have explored all of the physics and all of the kinematics and kinetics of the system. So in this case, we're gonna model contact center of pressure. And consider a contact situation, okay? We have these a partial drawing of a robotic system that is supposed to have a second leg making contact on the ground, but we are interested in this right leg and then what happens to this right leg. So we're gonna define several coordinates. One of them, we're gonna assume that the leg has a sensor, okay? It's a sensor located right here. Is a force sensor, for instance, an ATI force torque sensor, and it has a physical location inside the leg, okay? And we assign a frame, a sensor frame SI to this point. And also we are considering this red point, we're gonna call it the center of pressure for limb I, is for that particular contact, what is its center of pressure? And for that, we need to define what a center of pressure is. So it's a position of limb contact where horizontal moments are zero. It's a position that in the contact surface, you project all of your net forces and moments, the wrenches, and then they turn out to be the moments, the net moments are zero, okay? And this is ideas that were developed in the 1970s, perhaps, in Yugoslavia by Miomir Vukovatrovic, who passed away just a few years ago. And it led to a lot of the modern trends in locomotion and balance and stability of legged systems, okay? Now we're gonna consider the measurement of the sensor, okay? The sensor itself, the force sensor located in frame S, it measures linear forces and moments as well, okay? For instance, for a 6-dimensional force torque sensor, okay? This is called, FCI is the contact range meaning forces and moments, all right? If you use statics and free body diagrams and you develop a force statics analysis, you can obtain these equations. And we're not going over the elaboration of this equation, just the solution. That the location of your center of pressure, that point where the moments are equal to zero, it can be written as the location of the sensor, wherever it is located, minus this ratio of horizontal and vertical forces of measured by the sensor, times the moment arm defined by the distance, vertical distance between the sensor frame and the position of the center of pressure, and then minus this ratio of horizontal moments with respect to vertical forces measured at the sensor frame, okay? And the same thing can be done for the location of the center of pressure in the y-axis, the horizontal axis. It has a similar sort of static analysis, okay? Well, this will be important later because that we have to ensure that PI, the location, are within the support polygon of every limbing contact, okay? So let's leave this analysis on the center of pressure for a moment, and then we'll know that this is important. It's a constraint that the controllers need to fulfill, okay? There's more things, there are more constraints. And for that, we're gonna call a representation that was used for grasping in the past, and now we're taking it to legged robots, and it's called the virtual linkage. It's a mechanism connecting all limbs of all limbs in contact of a robot describing the relationship between contact ranges, internal forces, and center of mass acceleration. It's a little bit like an inverted pendulum model, but now for multi-contact, if you will. And that is a structure that I defined as part of my PhD postdoc, as a matter of fact, back in the late 2000s. So consider a robotic system making contact with the floor and with the table, perhaps. And the virtual linkage is defined here. It's a set of hinges located at the center of pressure of every link. And then there is these virtual prismatic joints interconnecting the whole network of contacts. And there is a dependency as well with the center of mass of the robot. Okay, it kind of relates all of these quantities together. That's what the virtual linkage model is. Okay, so here we have a close-up of the virtual linkage model, and for every center of pressure, we have the net forces acting on that center of pressure, which is the linear forces F contact 1, and we have also a set of moments acting at that center of pressure. For instance, another center of pressure, we have the net forces acting on that center of pressure, FC2 linear, and the moments as well. And also we're defining the tensions, the differential forces between the center of pressure 1 and center of pressure 2, and that's across the entire network of hinges that define the limbs in contact. Okay. Now, if you recall, the contact ranges are defined as forces and moments for every center of pressure for limb I in contact. And then we define already Fij as Fij are pairs of internal forces. Okay, that's how we call that. Okay. Now, without complete proof, you can use statics or kinetics, if you will, and Newton's second law, because you have accelerations as well, and not only like tension forces, which is statics, but then also you have effects of the reaction forces due to inertial behaviors. So you obtain this relationship. The contact range, forces and moments at the center of mass, and followed by concatenation of the vector of internal forces, is a function of all the contact ranges. Okay, if we multiply by something that it's in the past it used to be called the grasp matrix, and I rename it when I work on this paper in the late 2000s as the grasp contact matrix. Okay, in G is 6 times the number of contacts times 6 times the number of contacts. Okay, and it can be shown that the center of mass range is the inertial and gravitational accelerations of the robot, and the same thing for the angular accelerations multiplied by the inertia of the center of mass. Okay, and F int is just the vector, the concatenation of internal forces for every pair of limbs. And finally, FC is the vector of contact ranges for all of the limbs in contact. Okay, it can be further defined that the grasp contact matrix has a component that affects the center of mass, and a component of the matrix, the block matrices, that affects the internal force component. And then you can go in the literature and find that the WCOM matrix, it has this topology where things like PG is the location of the center of gravity, but the hat on top of PG is the cross product operator. Okay, and P1 and P and C are these hinges that we talk about, the center of pressure, the location of the center of pressure for every limb in contact, and the hat is again the cross product. Okay, so certainly a complex matrix. So I'm going to cut it here for a second, and details of the computation of WCOM and WINT can be found in this paper that I authored in 2010 in Translational Robotics, Comply and Control, Multi-Contact, and Center of Mass Behaviors in humanoid robots. We're going to take a break for a second. We'll be back. All right. So here we are back from the break, longer than what it looks in the video. So let me share the screen once more. All right. So here we have it. We studied now multi-contact, models for multi-contact that relate contact forces to center of mass and internal force behavior. And that leads to now studying stability of the contacts, contact stability constraints. And just before, we saw the relationship between the ranges FCOM and FINT, the list of internal forces, with being equal to the Grass matrix time the list of contact ranges. We can invert the Grass matrix, and now what we obtain is for a given center of mass behavior. Let's say we're accelerating, we're walking, we're accelerating the center of mass. Okay, that's a design parameter. We could argue that also design parameter is the internal forces between the limbs in contact, and that yields the contact forces, the contact ranges. So what we have to figure out is that if we're violating any stability conditions, we're losing balance or we are twisting something in weird ways through this equation. Okay, so we need to ensure that contact forces, the contact ranges that we saw for all the limbs, they fulfill Coulomb friction. For instance, range con constraints. And also that the contact center of pressure remain inside the contact surfaces, the support polygon for every fit, okay? So let's do that. In particular, we're going to consider two ratios. The first one is classical Coulomb friction, is the ratio between the vertical reaction forces for every limb and the horizontal reaction forces in X and Y. And then when we take the tangent inverse, what we're obtaining is the angle of the resultant forces, okay? Alpha CI. And what we say here is that the alpha CI, it has to remain within the friction con for every contact constraint. And we are assuming that we know it a priori. And the second ratio we're computing is the ratio between the vertical moments, the amount of twist of moments about the z-axis compared to the amount of reaction forces in the vertical direction, okay? And that's a ratio, it's not an angle, it's a ratio. And we use that as there is certain threshold, a rotational threshold or index that tells us where we are exerting too much vertical moments or not. And finally, the center of pressures for every limb, recall here we have one limb in contact, we have the center of pressure for that limb. We're not talking here about the center of mass or the ZMP, we're talking about every surface has a contact pressure for the resultant forces in that particular limb, and it has to be within the surface area, okay? The surface area is the bottom, this area here. And the question here that arises is, well, what happens if, for instance, the center of pressure, we approach it to the edge? So what happens is that suddenly we have the whole foot flips on this point. There is like a complete rotation from here to here of the foot sort of flipping over the frontal edge. And that, you could say, oh, I'm fine with that. Provided the robot is not falling on the ground, I can live with that. Okay, that's fine. So I'm not saying that it's something you should avoid, but a lot of the robotics that has been done today has wanted to have the feet completely flat against the ground. But if you're dancing, you are doing something sophisticated, you might want to walk the tip of your toes, or you want to walk on the heels, for instance, or on the edge of your legs. That's completely fine. So that finishes this segment on contact characterization, and the stability conditions for contact. We had the whole body dynamics. We talk about multiple tasks. Now let's present prioritized whole body control, okay? Which is a way to track trajectories given a priori, and then we can talk about it coming from an RT process, a trajectory generation process, for instance, and then how to do the best that we can to track those trajectories, and what happens if those trajectories are not trackable, all of them at the same time, right? That's why prioritization becomes important. All right. So what are some of the objectives of, and then those are inherited from operational space control. Some of the objectives, for instance, create compliant behaviors, which means basically scheduling impedance gains, and that can be very beneficial for safety. That's one of the properties of operational space control, and whole body control is a layer on top of operational space control. Unify force and motion and multi-contact behaviors. Okay, unified force and motion is something done with operational space. Now bringing multi-contact behaviors is what the whole body control does, okay? And then fulfilling constraints, geometric and contact constraints. Okay, that's something that whole body control does, okay? And other things that can come up from this is plan movements that are feasible given all constraints. And whole body controllers can go a step farther and be used as model predictive controllers, or as optimal control problems, or as trajectory generation problems as well. We're not exploring this here, but it could be another layer. So I also want to bring that you may know that inverse kinematics has been more popular, and one of the main reasons because people have models of the kinematics but not the dynamics often. For instance, but then with the emergence of locomotion, it turns out that locomotion trajectories require knowledge of the contact forces, and the contact forces require knowledge of the dynamics, and therefore that makes a case for the use of whole body controllers. Task priorities, they can also be defined in both in inverse kinematics or whole body control, and they allow to enforce safety constraints while executing multiple tasks. Okay, for instance, you can cancel the effects of an orientation task, for instance, a manipulation task where you're trying your orientation, if a set of joints approach joint limits. That's what you want to do, right? You are curling your hands, operating in the workspace. At a certain point, you reach the joint limits, and then you just stop, performing your orientation task because it's infeasible, right? And that feasibility is one of the characteristics of these prioritized approaches. Again, we're going to go into representation of skills. We saw that earlier. They are task coordinates, in essence, to achieve general for humanoids, locomotion and manipulation behaviors, and hopefully combine both of them together, okay? Here we have a table of, for instance, the behavior, where we have coordinates like joint limits, self-collisions, balance, hand manipulation, standing postures, internal forces. Coordinates we have is joint positions, distances, central mass coordinates, Cartesian, marker coordinates, tension, moments. So there's a whole variety of these heterogeneous coordinates And there is also a whole variety of policies, locking attractors, repulsion fields, pendulum dynamics, force and position control, capture sequences from motion capture data, optimal contacts, and you are throwing all of these to a whole body controller. That's what whole body controllers do. We're going back to bring up awareness of where task kinematics come from. It normally comes from something called homogeneous transformations. And for instance, if we go to the case of a planar 2D system, we can express the end effector kinematics as a function of the joint positions, and that's essentially leads to the Jacobian. Taking the partial of that matrix, it gives us of that vector. It gives us the Jacobian. And then we already talked that the task kinematics can be expressed as a function of Q dot only, ignoring the base kinematics. Okay, that was a recap, and Ji star here is the contact consistent as Jacobian. So what does it mean? It does mean that if we take the inverse, if we take a reference trajectory in task space and we multiply it by the inverse of the contact consistent as Jacobian, you obtain a set of robot joint velocity trajectories that comply with contact constraints. Okay, that's what it means that it's contact consistent. Okay, taking the inverse gives us consistent trajectories. All right. Okay, so we recall we're going now to prioritize torques. We're going deeper into formulating the whole body control problem with contact. If you recall, the whole body equation of motion, it was equal to this: the generalized accelerations, Coriolis and gravitational effects, some nonlinearity effects, and then we had finally the motor torques multiplied by the null space and the selection metrics. Okay, that was with the contact forces are implicit. The accelerations of the contact points are equal to 0. These are already a constrained analytical solution of the problem. Okay, and the problem we're facing now is how to choose motor commands such that task coordinates xi will follow reference trajectories. It's a trajectory tracking algorithm for body control. Okay, it's a trajectory tracking. What we're going to need to do is we're going to transform the whole body equation of motion into a task space equation of motion. Okay, and we're going to do that by left multiplying the above whole body control equation of motion by this term, UNC A minus 1. U the selection matrix, NC the contact null space A minus 1, the inverse of the mass matrix multiplied by the whole body equation of motion above. And if you do that, and I'm just writing here partial results, you obtain this term, UNC multiplied by generalized accelerations. Other terms, okay, that I'm not going to write because it's tedious. And then the right-hand side becomes the torque, which was multiplied by UNC transpose. And now you have a new term, UNC A minus 1, okay? Also recall that contact consistent joint velocities were equal to UNC generalized velocity. Okay, we've seen that multiple times. And if we take the derivative of these joint velocities, we're going to obtain something like that. Okay, that's the derivative of this relationship right above here, right, with generalized coordinates and joint coordinates. Okay, now taking these two sets of equations, we notice that the UNC generalized accelerations appear in both equations, and that yields this reformulated equation of motion. All right. And recalling that in terms of the joint accelerations, rather than generalized accelerations, now we have joint accelerations, okay? Now we recall that the task velocities are a function of the joint velocities if we use the JI star metrics. We take the derivative, yields this, and now left multiplying the above joint acceleration equation by J star, we obtain now what I want to call the operational space equation of motion, which relates xi double dot with the torques over here through these projections, okay? We narrow down, and now we have the accelerations of the task space, and that's the thing that we want to control. We want to control the accelerations in task space to follow our desired trajectory. So that leads to our theorem. Let's call it operational space control, in which we state that the following torque command yields linear control of task forces and accelerations. And here it is. Here we're using the content consistent Jacobian for the task I, JI star transpose F, and then we're using torque commands this way. I have the feeling that we're, no, that's fine, that's fine. That's fine, okay? And let's prove it. So we're gonna rewrite the operational space equation of motion as we just wrote it before. We're relating xi double dot with torque. We have other terms that I don't want to write because tedious, and then these projections. We're going to plug our control policy J star transpose F, and what we get is the relationship between xi double dot and F, and this term we're going to call it phi. Phi for the Greek letter phi. Some of you want to use phi perhaps. And it's known to be a symmetric non-full rank matrix. Okay. And now we're going to define task space mass matrix M star as the content consistent Jacobians phi JI star T inverse. And we're going to assume that it's full rank. Okay. The task is fully controllable. MI star is referred to as the content consistent task mass matrix, okay? Now, taking the equation above, now we have xi double dot F, and then just multiply by this term. It's just a rewrite of what we had before, but now with more compact notation, okay? Great, but because it's full rank, because MI is full rank, now we can choose an F that will yield a linear differential equation, which will let us do whatever we want with the task behavior. So, for instance, Corary, motion control. If we pick the control command, the above one, what we had above, JI star TF, and then we pick this policy. The force is MI star, this content consistent mass matrix, and then a reference command of accelerations plus other terms that I'm not writing them down, but the purpose is to cancel out non-linearities. This is feedback linearization. We plug it into our operational space equation of motion, and then this and this are going to cancel out. Other terms and other terms are going to cancel out, and then this yields exactly what we wanted. Is the actual joint task accelerations are equal to our reference command. Now the only thing we have to do is take reference accelerations as a PD controller or a PID controller, and we get the aerodynamics, which are linear. Okay, is a linear ODE, ordinary differential equation, where the error is x minus x desired, where we're gonna go, and then this is asymptotically stable. Okay, so we're tracking the trajectory perfectly. All right, that's what whole body control does for one task. Is we fulfill something great. Now we said we promised that we can control multiple tasks. So imagine two tasks, okay? Balancing and grabbing a ball at the same time, okay? Should we add them together? Would mean that we take a torque that is J1 star transpose F1, and then some other term that basically copies the same topology, J2 star transpose F2. And every Fi has the same motion trajectory that we saw before. Mi star AI reference, where Mi star is the constraint math matrix, okay? So if we plug this in the operational space equation of motion for every xi is related to tau and then this term. Okay, for instance, consider there's one operational space equation of motion for task 1. There is another operational space equation of motion for task 2. Now we're considering the first operational space equation of motion. We plug these values, M1A reference. Great, that looks good. But now we have a new term here, which is this thing, and then we have A2 reference. And it turns out that the second term is not linearizable in this form that is right now. We cannot cancel out, it's not identity, whether we were able to linearize the first term in first place, okay? So, so we say that A2 couples into task 1. It creates disturbances. These are mathematical disturbances, really. So it's not good, right? You want to have the best possible tracking possible, and then task 2 is interfering in task 1. So it doesn't work to just add them together. One solution is define a super task x12, which is a vector of x1 and x2. Here I'm using semicolon. This is the MATLAB notation. It's like stacking vertically x1 with x2. And that yields a super Jacobian that is basically the partial of x12 with respect to the joint coordinates. And that's going to lead to an operational space of motion of this compound coordinate x12 with a control tau. And then we can develop now a similar torque following whole body control rules. And then it will yield a linear control of acceleration. So great, we've done feedback linearization. We can do whatever we want. And it works. But this assumes that task 1 and task 2 are fully controllable. You can fulfill both at the same time. But what happens if they are not, obviously, okay? What happens in this case that you want to maintain the center of mass above here, and at the same time, that's your first task, you want to reach this point over here, okay? So, you cannot fulfill the two of them, as we can see here, right? You either fall and or jump or something, or you don't reach the point that you want, okay? I want to point out that whole body control, it can always be expressed as an instantaneous optimization problem. In this case, you're minimizing your current accelerations with respect to your desired accelerations, and then you're fulfilling the operational space equation of motion. Okay. So if there is a conflict, then you're not nullifying the cost error. You're just approaching it. But then in this case, you're not balancing well. You're not reaching the ball well, so you're failing in the two counts. So this yields to a little bit more of a background on algebra. We're going to make a little bit of parenthesis here to just solidify the knowledge of null spaces, and that will allow us to solve the problem we were just solving a moment ago. Consider a matrix, a square matrix, and consider the equality that AX is equal to 0, what is x? What vectors make this product equal to 0? So the set of vectors that nullify the product are the ones that belong to the null space of the A matrix. And then one quick way of obtaining vectors that live in the null space of the A matrix is to take this this product. X is equal to identity minus the pseudo inverse of A times A, and then any vector, any arbitrary vector Y fulfills that. And this term, I minus A star, A plus A, is called the null space of A. So why is the null space? Because A of X, if we substitute X by the null space Y, well, A times I minus A plus A is equal to A. So we have A minus A and is equal to 0. All right. So that's why this is a null space. And that's why you see these forms of null space. All right. So now that we are a little bit more knowledgeable of null spaces, instead of summing, we had two tasks. They were conflicting. So we're trying to organize priorities perhaps. So we're considering the alternative that the first task, we'll leave it pretty much as it was originally. And the second task, we multiply it by a null space. And the null space, we're going to call it N1 star transpose. N1 star transpose is similar to the null space we just defined, a little bit more sophisticated. Is I minus Ji star transpose bar, which is a generalized inverse. So this is the null space of the Jacobian Ji star transpose. Okay. And we might have said that before. Ji bar transpose is a generalized inverse of Ji star, and is the matrix phi times Ji star transpose, and then the content consistent Mi star matrix. If we recall, the operational space equation of motion was xi double dot as a function of tau. We wrote it in a more compact way here. It can be shown that if we employ the torque command above, we're getting x1 double dot is equal to A1 reference. That's a linearization that we're looking for. And the second task, because it has the null space, is being multiplied identity by J1 star phi, and the other term is J1 star phi, and then by whatever was there before, J1 star transpose, M1 star, J1 star phi. And then this, it can be demonstrated that this is equal to 0. Okay, algebraically is equal to 0 because this term here is Mi star minus 1, which cancels with Mi star. And then essentially we have J1 star phi minus J1 star phi, which is equal to 0. So we've accomplished, we don't have any more coupling of the secondary task on the first task. Great, we solved prioritization, have solved that problem of no coupling. Now we need to do a good job at controlling a second task. So let's consider, for instance, we have the first task as we defined above. Now we have the null space, okay, that's same as before. And now we're just going to implement like a PD control law for the second task. Let's say we're controlling we want all of the join positions to be equal to Q desired, okay? Now, this is conflicting clearly with the first task being something like moving the arm or something, because we cannot control all of the joins at the same time that we control something else. We're using more degrees of freedom that we can afford, because X1 is commanded to follow a separate trajectory via this command. Okay. So for example, if X1 is tracking a ball, okay, here we have X1 is tracking a ball, and X2 is maintaining a posture, Q desired. What is a posture? Well, a posture are all of the degrees of freedom, okay? So that's what is X2, is all the joints. Clearly, you cannot fix the robot in one pose because that fixes the entire robot. So the robot couldn't move down, right? So you have to give up in something, right? Then, but then because X2 belongs to the null space of 1, it will not enforce the posture fully. Like N1 will kind of remove some of the posture degrees of freedom. So the arm, because it's first priority, it will fully reach the ball, but then the rest of the pose will depart. And that's fine. That's what you want to do. Except that what you want to do is that the pose, given that it doesn't reach the exact value that we're providing, we want it to approximate as much as possible. We want to be asymptotically stable towards the minimum possible value. Okay. So that's it here. We would still like to minimize the error. Okay. By selecting an appropriate secondary control command. So if tau2 is simply this PD control law, this was demonstrated in Oriolo 1994, this paper over here, ICRA. It was demonstrated that if the error on the posture is in the null space of, then the error gets stuck and never achieving its minimum. On top of that, N1 star transpose yields very poor convergence rates and yields to awkward poses or awkward configurations for infeasible secondary tasks. And then in this paper, Peterson and Sentis 2013, we show a better solution, which is to compute secondary torques as J2 bar 1 star transpose, where we define J2 bar 1 star as J2 and 1 star. Okay, is the multiplication, is a prioritized, we call it a prioritized Jacobian. Okay, and with that we also define a correction matrix N21 star. That's all we have to do, define this Jacobian and define this revised matrix. The control policy is the same. It's a PD control law on the joint configuration. And here is the mass matrix. It's J21 star phi, which we saw before, J21 star transpose minus 1. We call it the prioritized mass inertia matrix for task 2. And then we recall that operational space equation of motion was xi double dot as a function of tau. If x2 is q, is the joint positions, right? It's a posture task. And let's assume for a second that the first task has already arrived to its destination. So F1 is equal to 0. So we don't have that effect. But you know, this generalizes for all the cases, but it's easy to explore it this way. Then the operational space equation of motion for the second task, which is the joint task, it takes this form. It's phi plus phi J21 transpose F2, which results on this phi J21 star transpose. And this we're going to call it phi to 1 star term. And I'm not going to go into the details of all of these formulations, but it can be shown that this is not full rank because the second task is not fully feasible. Otherwise, we just would do feedback linearization and we'll control Q double dot directly. So, okay, do we still get an advantage? So we're going to choose a control policy that is, in essence, is going to be phi to 1 star, this matrix, and then a pseudo inverse, not an inverse because it's not invertible, but a pseudo inverse times A2 reference. What does it do if for the second task we choose this policy? What part of Q double dot will be controllable? Okay. Now we're going to consider the singular value decomposition of phi to 1 star as U sigma U rank. What is, when we have the superscript rank, it means that the sigma is full row rank. So for instance, the eigenvectors U rank, they're not square. The dimension is n minus n1, n being the robot joins, and n1 being the coordinates of task x1. And this n minus n1 is the degrees of freedom that can be control of the secondary task. We're removing the first degrees of freedom, and that's what we can control. Okay? It can be shown that with this projection, what you get is that the eigenvalues U rank Q double dot is equal to the eigenvalues U rank transpose A2 reference. You cannot cancel these matrices out because they are non-square. And A2 reference is a PD controller with our error term. And that, if you look at it, it almost looks like a linear matrix. In the subspace, U rank transpose Q double dot, okay? So we almost have linearized it. It can be demonstrated through Lyapunov theory that this controller will be asymptotically convergent to the minimum achievable of Q minus Q desire, which is different than 0. All right? And that leads to a very well-behaved, it's doing its best that it can, the secondary task, okay? And then if it's feasible, if you choose another secondary task, it wouldn't be the whole degrees of freedom, it would be like a subset of them. Then both of them will be accomplished perfectly. It will be perfect tracking for the two of them. Only when they have conflict, the second task does its best possible job. In conclusion, stacking tasks can lead to conflicts. Priorities solve conflicts at runtime. Now, this leads to a couple of questions. Do priorities increase computation times? The answer is no. In fact, they decrease the computational time since the problem breaks down operators into smaller dimensions. So our experience is the more priorities, the higher the computational rate. Question, who uses priorities? Well, they're used in many places. They're used in, for instance, in DLR in Germany, possibly Boston Dynamics. Simpler versions of prioritized whole body controller are used in MIT's Cheetah robot, and I know that because one of my students went there for a postdoc and implemented those. And that's what it is for two tasks. And for the final part of this lecture, we're gonna generalize prioritize multitask control to more complex behaviors. Suppose we have this is like a ladder, like I think I took this picture from, it was a ladder on a garden, on a playground, and then the robot was assembling it with nails. And we saw there is a number of tasks: balance, manipulation, gaze, posture, each of them with the coordinates and a policy and degrees of freedom, controlling all of these degrees of freedom. As you can see, the last posture controls all of the degrees of freedom, which clearly conflicts with the others, okay? But then, you know, balance and manipulation might conflict, and then the priorities are gonna kick in when this happens. Every task is expressed as an xi. For instance, the hand task, it has hand position and has hand rotation coordinates. We define prioritized Jacobians, here we have it, with content consistent prioritized Jacobians, as we saw before. And now for two tasks, we said our policy is this: tau1, J1 start transpose, F1 plus J21 start transpose F2, with F2 having this prioritized mass matrix and also having this prioritized content consistent Jacobian. Now, if we have prioritized over multiple tasks, we're going to extend that. We're going to call it tau is tau1 plus tau21 plus tau321 plus tau nt, number of tasks, and then proceed with followed by the preceding tasks. What is this preceding I operator? It's just the list of all previous tasks: 1, 2, 3, 4, I minus 2, I minus 1, whatever precedes task I. Okay, that's what it means. We're prioritizing torques over the preceding task. So here's our second theorem: prioritize multitask control. The following tracking control policy will yield linear control of all tasks if they are all fully controllable. And here it is: tau I preceding I, the control policy for task I, prioritize with all preceding tasks, is this prioritized Jacobian Ji preceding I, Fi. This Ji preceding I is nothing else than the Jacobian of the task multiplied by the null space of all the preceding tasks. And the forces are multiplied by this prioritized mass matrix, Mi star preceding, prioritized with all preceding tasks. And it can be shown that an equivalent and faster form of the prioritized null space for all previous tasks is the identity minus the summation of the inverse of J multiplied by J. That's the null space that nullifies all previous Jacobian, not just one. It's an interesting algebraic property. As a result, if we formulate the problem, all the operational space equations of motion are formulated here for every task. It can be proven that all of them will be linearized if they are fully feasible. And as a corollary, if task I has priority greater than J and there is a conflict, then in theory, task I should be accomplished fully and task J should be optimized as we saw earlier. So the lower priority task will only be minimized. So in such case, it can be demonstrated that the prioritized Jacobian Ji preceding I is full rank, fully controllable for task I, because that's feasible, because task preceding I don't contain J has lower priority, but the prioritized Jacobian for task J is not full rank, singular, because it's not fully controllable. This is a conflict, since the preceding tasks to J include I, and the result is such that task I is going to be asymptotically stable towards zero, whereas task J will be stable and it will converge to the minimum possible. Is achieved. The minimum of xj minus xj desire is achieved. And that's the best thing that it can happen in such cases. For instance, we have here Asimov, what would I work with in my PhD, is trying to control task 1, the center of mass, and that's with priority 1. And then the task 2 is to follow certain trajectory with the foot. Well, at time equals 1, the center of mass has to remain here, and then it has stretched completely the leg. It cannot move farther. So because task 1 has priority higher than task 2, what we'll see is that the leg will stop once it reaches a singularity, which is the leg fully stretched. Automatically will stop, but it will not fall, preserving the safety. This can be explored using the condition number, which is the ratio between the highest to lowest singular value of any metrics. So if we take the condition number of the center of mass, prioritized center of mass, we see that it's well behaved because it's fully controllable. But if we take the condition number of the foot prioritized, we're going to see that it shoots to infinity. And that's when it becomes uncontrollable. And then that's when the priorities should kick in. And then we have this convergence to the minimum possible value. So as a result, the food will automatically stop. And maintaining the safety we're looking for. Now, I want to finish with an observation. Why using prioritized feedback controller if motion planners can design trajectories that do not conflict? The response is because planners give updates at much slower rates, sometimes 100 times slower or or even more. And therefore, we'll encounter divergence between the desired trajectory and the actual state. Whole body controllers are feedback controllers really fast, and they can add this robustness where for those milliseconds that the motion planner is making a mistake, it can allow to have safety and then robustify the whole behavior. So that's why you see normally a coupling of a motion planner with a whole body controller because of these levels of robustness. You can find videos in these links of these effects. And that was pretty much it for this lecture. And it's been a pleasure to be here today with you guys. I wish I was in person. Demetrius, thank you for inviting me. I hope that this is useful for everyone. Otherwise, I'll see you very soon. Bye-bye.